let's say that I want to make a circuit that outputs a digital one if I receive the first letter of my first name from a keyboard using the ASCII2 character set or through the internet, something. So the first thing I got to do is I got to look up on the ASCII2 table what is a lowercase t, what is an uppercase t. You will do this using the letter of your first name. Then the first thing I got to do, remember the parity bit. So even though in the ASCII2 table from the example, it always starts with a 0, in reality, the first bit is a parity bit. So let's say that we have even parity. Even parity just means that in a byte, I'm sending an even amount of ones, right? So I go 1, 2, 3, 4. 4 is even, so my parity bit is going to be a 0. 1, 2, 3. So that's odd. My parity bit has to be a 1 to keep it even. So basically, I need to send 0, 1, 1, 1, 0, 1, 0, 0, or I need to send 1, 1, 0, 1, 0, 1, 0, 0. So I need to send either one of those. So to do this, I'm going to have 8, 1, 2, 3, 4, 5, 6, 7, 8 address lines. So this is the address bus in your computer. Or it could be how it gets sent. So if you have a parallel collection, you would send this kind of in one. If you have a serial connection, you send it in a stream of ones and zeros. And then we're going to use memory device, the flip-flops, to actually store them and then bring them out so we can look at them all together. But we're going to use 8. So I have 8 for my lowercase t. I have 8 for my uppercase t. So my lowercase t, 0, 1, 1, 1, 0, 1, 0, 0. My uppercase t, 1, 1, 0, 1, 0, 1, 0, 0. So if I receive this, I get a lowercase t. If I receive this, I have an uppercase t. How do I give a 1 if I receive either one of those? So if you become an electrical engineer or a computer engineer, you will actually take an entire class in how to do this the most efficient way. So we're going to show you a really easy way that's not the most efficient way. So the easiest way is turn everything into ones. So remember on your logic gates, a NOT gate using one transistor will turn a 0 into a 1 or a 1 into a 0. So basically, every time I have a 0, I'm going to just put a NOT gate. So bam, so now my output if I had this, 0 turns into a 1, 1 stays a 1, 1 stays a 1, 1 stays a 1, 0 turns into a 1, 1 stays a 1, 0 turns into a 1, 0 turns into a 1. So now I have all ones. All of my 8 lines on the address bus are ones. So now I need to combine them. Any gates that take 2 ones and turn it into a 1? An AND gate. Let's use an AND gate. So I'll take these two, combined with an AND gate. These two, combined with an AND gate. These two, combined with an AND gate. These two combined with an AND gate. So now I'm down to 1, 2, 3, 4 ones given this input. Okay, I keep combining them. 2 AND gate makes an AND gate. 2 AND gate makes an AND gate. 2 AND gate makes an AND gate. So basically, in this scenario, I have a 1 only on this input right here. So now I'm going to do the same thing for the second one. So 1 can stay a 1, 1 can stay a 1. Anytime I have a 0, I'm going to take a NOT gate, and I'm going to invert it down. So now I'm going to have all ones given this. All I did was Whenever I have a 0 input, I use a NOT gate to convert it to a 1. Okay, now I can use AND gate, so I combine them. 2 ones on an AND gate becomes a 1. 2 ones on an AND gate becomes a 1. 2 ones on an AND gate becomes a 1. 2 ones on an AND gate becomes 1. Okay, let's combine them. 2 AND gates on an AND gate, 2 ones gives a 1, 2 1 gives a 1, 2 1 gives a 1. So now I have a 1 on a lower t, I have a 1 on a capital T. Okay, I want to give a 1 if I have I can't give a 1 if I have a 1 here and a 1 here because I'm not pressing, I can't receive these two signals at the same time. It's either a lower t or an uppercase T. So I'm going to use an OR gate in the end to combine them. Remember, the OR gate has kind of lowered back down. So now I have a circuit. This is the circuit that's going to give me a 1 if I would receive a lower t or an uppercase T. So how many transistors? So I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 NOT gate. Each of them is, remember, 1 transistor, 8 transistors. Then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 AND gates. And each AND gate, remember, is 2 transistors, so that would be 28 transistors. And then I have 1 OR gate. That would be 2 transistors. So totally, in this circuit, I have 38 transistors. So if I had 38 little transistors, I could build exactly this circuit. Now think that I have about 127 different characters on my keyboard, right? So I can go 38 times 127. It would be about 4,826 transistors just to recognize what buttons I'm pressing kind of on a keyboard. So a lot of transistors. If we start using memory, remember when we looked at flip-flops on that assignment, we use many, many, many more. Each memory device is, I think, 1, 2, 3, 4, 5, 6. So 12 transistors per memory device. So if I needed to even like store each of these guys before I did anything, it would be 12 times 8 transistors just to store that information. So you can see how we need millions or even billions of transistors. So anyway, that's how you can make a combinational circuit. This is a pretty inefficient one. Again, you would take classes on how to make the most efficient one using AND gates, NOR gates, NAND gates, all of that kind of stuff. They use a method called Karnaugh maps on how to do that. But check it out, though. Even before I start this, if I look at mine, right, I could have made this a lot smaller to begin with, because if you look at my circuit up here, what are the two different things? The third bit is different, and this bit is different. So basically, I could have saved a lot of them because these guys, 6 of the 8 are always the same. So I could have saved a lot of these even by doing that. But that gets a little bit more advanced. So for now, just do the first letter of your first name, lowercase, uppercase, look up the ASCII2 code, add a even parity bit in front of it, turn everything, once you have your 8 address lines, like the address bus in any computer or any circuit, once you have those, start turning all the zeros into one, AND gate everything together till you get down to one AND gate, and then your lowercase and your uppercase, you just OR gate together. That's all there is to it. If I wanted to, another little thing, let's say I wanted to give a 0 instead of a 1, right? In the end, a 0 output, if I got a anything else, I would just put a instead of a OR gate, I would put a NOR gate on the outside of it. And you can also see, let me show you an example. Let's say that this guy right here was a 1 instead of a 0, right? Let's see what the circuit would do. So let's say that this guy is a 1. So my 1, 2, 3, 4, my fifth bit is a 1. What is this guy going to do, right? 1, 1 on an AND gate gives a 1. 0, 1 through a NOT gate becomes a 1. 1, 1 on an AND gate is a 1. 1, 1 on an AND gate is a 1. So I have a 1 to write here. 1 through a NOT gate becomes a 0. The 1 stays a 1. 0, 1 on an AND gate is a 0. 0, 0 through two NOT gates is 1, 1. So I have 1, 1 on an AND gate gives a 1. 0, 1 on an AND gate gives a 0. 1, 0 gives a 0. So right here, I would have a 0, right? Instead of a 1 if this bit has changed. And similar up here in this case, even let's say that this guy had stayed the same, we'll change it to, if this guy was a 1, 0 through a NOT gate is a 1, 1, 1 on an AND gate is a 1, 1, 1 on an AND gate is a 1, 1, 1 is a 1, 0 becomes a 1, 2 1s on an AND gate becomes a 1, 0, 0 through two NOT gates becomes 1, 1, 2 1s on an AND gate is a 1, 1, 1 on an AND gate is a 1, 1, 1 is a 1, right? So here I would have a 0 or a 1 on an OR gate would give me a 1 output. So if I had received something wrong on the uppercase T, but my lowercase t was, hold on, if it changed to 1, screwed up. If I change this to a 1, I would have a 0, this guy would be a 0, this guy would be a 0, this guy would be a 0, 0, 0 would be a 0 on an OR gate. I've got to change the one that I changed right there. So if I had received one of the bits wrong, it would be another character, and I would not generate that one for my output. So I hope this kind of makes a little bit sense. This is a little bit above the scope of our class, but I want you to kind of understand why do we use so many transistors in computers. And this little example is just for addressing, just for like figuring out what did I actually press to do something on.